Today we are going to speak about fast and approximate responses, but first of all, a few words about me. I am Артур Соловьёв. I am a software engineer with the main interest in algorithmic trading. By the way, everybody knows what algorithmic trading is, right? Right. Good enough. So stocks buy low, say high, sell high, yeah. So we need to respond fast in our domain, and I think I'll show you a few techniques which will have you more prepared in responding fast as well, and hope you like it. So what is our problem? Fast and approximate responses means we need to respond fast, usually in real time. For example, in self-driving cars, if we don't process data fast enough, then car will crash. In video games, that means game will stutter. And in optimal DL, getting back to our thematic, subjects, the documented application, document estimation, and calculating daily average users, and so on. All those problems require to respond fast and require to, preferably have a constant or not so much space, and that is what I'm going to show you now. And what else I wanted to say. So the solution is to use probabilistic data structures. Anyone knows what probabilistic data structure is? Please raise your hands. Yeah, not too much, but I think we'll handle it. Yeah. So sometimes we cannot allow ourselves to answer in time or space depending on the number of elements. Let's say we have 100 of elements and our answer time is 100 nanoseconds. That especially happens in financial sphere with exchange orders. But when the number of elements grows, when it's like 1 million, we still need to respond as fast as we used to do with 100. And that basically means compressing linear solutions into constant ones. But for cardinality reasons, that is not possible entirely. I mean, there's no ideal compression. If you try to, let's say, compress 1 million elements into 1,000, you simply cannot do that ideally, and your compressor will inevitably lose some information. That is why probabilistic data structures often lose information, and we really need to know which profile our queries have, because we need to use upsides and downsides of each structure, and that's exactly what we will consider for now. I won't bother you with theory, only real applied tasks and only real solutions, and sometimes you'll have code. The slides will be named "Try Yourself," and you can try yourself, probabilistic data structures. So let's start with problem 1, if element in set. Problem sounds relatively simple, right? So to answer precisely, we need to store all elements. That means linear space. And that usually means our RAM usage will grow indefinitely when we try to store all the elements. For example, to answer precisely on is Twitter post contained in our Twitter dataset. If the dataset is 10 million elements, that means we need tens of gigabytes of RAM, and that is something not suitable for us. But there is a solution. The solution is to have a constant size structure, which will map one bit of structure to many elements of set. And let me provide an example, and that is balloon filter. Okay, forget that slide header for now. I'll explain you the principle. Let's suppose you have a gym and number of visitors is not always constant, It's like gym can be visited by 10 people at a time, 50 people, 100 people, and so on. But the number of lockers is always like 10. And one locker fits many belongings, and your gym buddy, by the way, who visits gym regularly. Why are you doing like that? Okay, I've got it. Yeah. So you have a gym buddy, he has a favorite locker, and what exactly that means? When that locker is empty, that means your buddy definitely not here. But if the locker is closed and it contains something, you need to do an additional check. You need to visit the entire gym to find your buddy or not, to be sure. And that is exactly how Bloom filter works. It's a set of such lockers, and each locker can be either 0 or 1. And if the Bloom filter bit is 0, that means there's no such element. And if there are 10 elements mapped on that bit or on that locker, it means no one is present here. And that solution is, and that feature is required in some real-world problems, such as document deduplication. Because let's imagine you have a data set consisting of millions of entries, and you need to know which of them duplicate each other. Generally, there won't be many duplicates, so most of the time the response on whether element already in set or not will be false. So that is the use case for Bloom filter. And how does naive solution, don't bother with it for now, how does the naive solution sound? The naive solution is to store the entire set and to check it each time. Let's say your set of, tweets doesn't fit in RAM at all, and you drop it on a hard drive. Hard drive latency is like milliseconds per entry, so that means you'll be very slow. Or otherwise, you'll have not enough space in RAM to store all the entries. So instead, you can do the following. You can add your entries to the Bloom filter along with adding them in set. And Bloom filter goes in RAM, and your set goes on hard drive. Usually, you get a Bloom filter entry which is negative. There's no such tweet in the set. There's no such element, and you won't bother checking HDD at all. But in that 1% of cases where it happens, well, you'll get slowed down by 1 millisecond, but that's only like 1% of cases. The thing is, the original solution included either getting linear space and having the entire RAM filled with elements, or dumping those elements in the HDD and therefore getting too slow. And this solution means we get both faster and both save a lot of RAM, because in RAM we contain only Bloom filter, which is like hundreds of megabytes instead of like tens of gigabytes. And on hard drive we contain a full set, and full set is something we address relatively rarely. And that is why we answer now both fast, and we don't take much memory. And for practical reasons, for learning reasons, that may mean difference between like 8 hours of training and 1 hour of training, if you read from RAM or you read from hard drive. Or it can mean a successful train or an out of memory, if you place the entire set in memory against placing only Bloom filter in the RAM. By the way, getting back to solving collisions, let's suppose we have a collision in the gym. Our buddy always visits gym at the same time with some other guy. which likes the same locker as our body. And what we do then, we have two rows of lockers. The first one used for, let's say, shoes, and the second one used for other belongings. And we know probability of, how do you say, probability of those two persons colliding both in shoes locker and other locker, it diminishes really fast. That fast, so on 4 rows of lockers, you will get like 2% error. And that is what you generally do with when dealing with probability data structures. You simply add more structures. You simply add more hashes, more rows, be it called bits or registers, and that will be the general approach. So to summarize, Bloom filter is when you have mostly negative results. Bloom filter lets you save a lot of memory because you build index using Bloom filter, which is relatively small, and then you dump all the remainder, the original set on HDD, and you address it relatively rarely, which saves you a lot of time. The second problem, which sounds relatively easy again. By the way, don't pay attention to number of orders. Sometimes the presentation can be quite deceiving. That is because it's from another speech. So if you don't understand something in presentation, just simply listen for me. I'll explain. And the most, we have a problem of maintaining set, and we have a problem of estimating cardinality. And maintaining set and giving a precise response on how many elements in set means we need to store all the elements. And yeah, I understand you already want to have a random beer and something, but let's sit for a few minutes, and we'll meet again. I hope so. Yeah. So the problem is to estimate set size, and we can solve it either in linear space or in constant space by estimating cardinality. What is the real-world application is counting daily average users, for example, because in analytics, streaming, processing, big data, usually you take into account like millions or even billions of users, and it's not like you can always afford to maintain the entire database of users. So you estimate their number using constant space and constant time, and the principle is, I'm going to explain, but you can have a look at the slide as well. The principle is you are trying to meet elements which are relatively rare in stream. That means, for example, if you count elements with like 20 leading zeros often enough, then it means the set has like 2 power 20 elements. It's like approximately a million of elements. And that is precisely how hyperlock works. You simply count the unique elements with n leading zeros, and you somehow average them, average the results. Actually, it's not like average formula, but I won't go into details. Let's say it's another story. Yeah. So for downsides, I think it's quite obvious. It won't work on a too small set. So you need to either get more hyperlock locks, combine them, or you need to like use a hyperlock lock on a set that is big enough, and that's basically the main use case. You can try it yourself. The thing is the example before doesn't cover adding to the set. And adding to the set is something which is quite time-consuming and space-consuming. Time-consuming because worst case is rehashing, and on millions of elements that can take much time. And aside of that, you can use hyperlock lock. Instead, you'll get constant space and constant time. And you, in a Python package hyperlock lock, you can even set the margin of error, how exactly you want your hyperlock, how precise you want your hyperlock lock to be. We have another problem for now, which is it's not document deduplication. Deduplication was a problem one, but that doesn't matter for now. Document similarity. Yeah. So someone has any clue about how do you estimate similarity of documents? Please raise your hands. One. Another. Yeah, now see it's open data fast. Good enough. Yeah, so shortly, classical solution is to tokenize our text, split into trigrams, and then calculate Jacquard similarity. I won't get into details again. So shortly, we have document data science. We split it on trigrams. And then when we get the document data scientific, many trigrams intersect. And the elements, it seems to be documents are relatively similar. But if we have something like calendar data, only one trigram matches, only two ones, date and ATA. Yeah, so documents are not that much similar. So the approach is relatively okay, but on large-scale solution, that means too big elements, too high amount of documents, or how do you say, document size will cause either one dimension or the other one to grow. And given we need to compare documents pairwise, that actually means something like quadratic space and time, which is unacceptable sometimes because we simply don't have that much memory and CPU time. What is the solution? There is a technique called min hashes, and it allows us to reduce our n-gram hashes into fingerprints. Fingerprints are a minimum of hashes taken on a couple of trigrams. Min hashes have that important feature, which is called locality sensitive hashing. That means for many documents, if they are similar themselves, then their hashes will also be similar. And that means we can reduce our documents to a constant hashes and then compare those hashes to get an estimation of document similarity, which is good enough. And that what is this slide is about. Okay. What else? You can try it yourself. sklearn, by the way, who used sklearn at least once in their life. Again, data fast. That's exactly what I expected. Yeah, good. So sklearn LSH forest. That is not exactly min hash, but it uses similar principle of locality sensitive hashing. So if you compare hash fingerprints, it means if they match, then documents themselves match as well. I actually don't want to go deeper into that problem, but I'll try to. So someone knows a thing or two about exchanges, financial, Wall Street, like stocks, securities, derivatives? No. Okay. Okay, so there is a kind of crypto exchanges which allow you to buy cryptocurrency, and they usually give you a set of proxies you can use to connect to them and to buy or sell crypto. But for some strategies of algorithmic trading, when you buy low, sell high, you need to know what exact latency is between you and the exchange, and it's not that easy to measure. Naive approach is to calculate quantiles, but let's say it's time and space consuming as well. How to measure it? No, I need the other side. Yeah, you can maintain distinct sets of quantiles, but that is let's say it's difficult and it takes much space. And the most important thing is it's hard to do that on stream, so in real time. So, by the way, how to measure the resulting latency? Yeah, I think you'll get this slide very well. I don't even need to say anything here. Many models of network latencies are like identical and independently distributed. Total latency is some of those latencies, and someone knows what that means. Someone knows it means they converge to a normal distribution. Someone doesn't. Okay. Thank you for your honesty. I guess, yeah. So there is another solution, which means we approximate our quantiles by using fast quantile clusters. That means each new element not just gets added in some kind of sets, but instead shifts that fast quantile a little bit. We don't store all quantiles now, element by element, but instead store approximations. And now let's have a look on this chart. It means kinds of errors which affect our latencies. I'm sorry about P95. That's definitely not P95, but it's just for verbosity. So generally, we have a good case of latency between one machine and another when everything goes fine, and we have a couple of bad cases like routing errors, packet loss, and so on, and we need to prune them. And only then we need to find mean. And why mean equals median in normal distribution is, I think is something you know as well. If not, then I'll be quite surprised, but okay. Yeah. So you can try those rolling quantiles themselves yourself. You can find median like right now, or you can do a 95th quintile pruning first, and only then you can find median, because rolling quantiles support pipelines of quantile search. So about other real-world applications, I have said about a couple of real-world problems and solutions, and Redis Bloom and Apache Data Sketches more or less supports solving them all. Also, they both can estimate number of frequency of element in a set using count min sketch, but that's for another day. And Apache Data Sketches also knows how to do set intersections and set unions on a stream without storing the sets themselves. So you definitely need to try it yourself. And about sklearn, yeah, I've already told you that. Similar aspect with min hash, which is local sensitivity. So what is the best practice here? On a large scale, on a big enough documents or a big enough number of documents, you don't need to compare documents themselves, but instead use locally sensitivity hashes and compare them using hashes. Sometimes this technique is the only one which allows you to, measure document similarity, duplication, and so on, because other ones simply don't work on that much on that much number of data, which we have in case of, let's say, web full text search and so on and so on. And as far as I remember, similar principles were used in Alta Vista and some similar search engines from the 1990s. But that is story for another time as well. I'm sorry for saying it all the time. It's just I have only like 20-25 minutes, so we need to be pragmatic. Uh, Ладно, окей. Yeah. About common principles, you already know them. A couple of structures which generally don't calculate the entire set, doesn't store all objects, doesn't compare objects, only compares fingerprints, and gets combined with similar structures for better accuracy. Also, just two more things. For uniform load of such kinds of structures, you generally need to store not elements, but their hashes, just in classical hash sets and hash tables, you know. And what else? And now it's questions time. And I think if you want to have a random beer before, you must ask at least one question. So here you go. Yes.
Thank you for your speech.
Yeah, thank you. What's the question, by the way?
Привет,
Привет.
Александр меня зовут. А вот некоторые базы данных в высших 16 битах указателя, в 64-битных архитектурах хранят Bloom-фильтр. Вот у вас в трейдинге похожее решение используется?
У нас в трейдинге используется запрятывание в указатели, в младшие биты указателя на то, что маркера того, что прямо сейчас элемент, а вернее указатель, используется каким-то другим агентом. Это называется hazard pointers. А что касается запихивания туда какой-то еще информации, ну да, если у вас, скажем, указатели aligned по размеру страницы, вы знаете, что младший там n-бит вы можете туда что-то запрятать. А теперь, внимание, вопрос. Понял ли я вопрос?
Использованием вот этих глобалистик структур, как помогают они?
Случалось, помогают, но в целом мы не запихиваем бум-фильтры в указатель вместе с каким-то, с какой-то датой, мы просто храним битсет, и это, ну, фильтр. Я просто подумал сначала, вы говорите про то, чтобы хранить информацию какую-то в указателе полезную, еще в старшие биты запихивать бум-фильтр. Нет, так мы не делаем. По соображениям сложности и психического здоровья людей, которые бы кодали это.